Hello everyone, welcome to Engineered Learnings. Engineered Learnings has been created as an effort to help and reach out to all the engineering students, aspirants and professionals out there with the basic understanding and the crux of the topics important for placements, Vivas, semesters, competitive examinations and all types of interviews. So let's go to today's topic. So what is continuous stirred-tank reactor? Any continuous reactor is something that has a steady state process. That is, there is no accumulation in the system. Whatever is going in is coming out of the system. But a reaction is taking place within the system. Here I am considering a reaction of A to B supposedly with a reaction constant of K. Let it be a first order reaction for consideration as of now. If it is a second order reactions, the things are going to change up a bit and things are going to get a little more complex, but considering it to be a first order reaction, so A is getting converted to B. So A is entering the first reactor with the concentration of Ca0 and a flow rate of Q total. So the number of moles of A in the inlet stream is Q into Ca0. And in the outlet stream, the concentration of A is changing. That is, it is getting decreased because some amount of A is being converted to B. So A concentration is decreasing in the solution, B concentration is increasing in the solution. So Ca1 will be less than Ca0, but the flow will be the same as I already mentioned, that there is no accumulation in the system. Whatever is coming in is going out. It's just the amount of B and A that is decreasing and increasing. That is, in the inlet stream there is pure A and there is no B. But in the outlet stream there will be some amount of B involved and there will be a lesser amount of A than in the inlet stream because some A has been consumed out. And now this is the fundamentals of a CSTR, and it is a continuous stirred tank reactor. This is the agitator system that continuously stirs in the reactants so that they can react among themselves and produce the products. And it is a continuous process as we can visualize. Now talking about CSTR in series, as I was talking about, that the exit of one CSTR acts as the entry of the other CSTR. That is, if I enter something, supposedly I am entering 5 moles of A. In the first reactor, the 5 moles is becoming 3 moles. In the second reactor, the entry of A is going to be 3 moles of A. From the second reactor, supposedly when I am exiting, I am getting 1 mole of A remaining. And in the third reactor, we are seeing that 0.5 moles of A is reacting. So we are entering with 1, we are exiting with 0.5. So what was my initial number of moles of A? It was 5. At the exit of this first reactor, it became 3. At the exit of the second reactor, it became 1. At the exit of the third reactor, it became 0.5. So we are seeing as we are proceeding, the concentration of A is changing and the exit of one CSTR acts as the entry of the other CSTR. So we will have to remember that Ca0 is the concentration that is entering the first reactor, Ca1 is the concentration of A that is exiting the first reactor and entering the second reactor, and the Ca2 is exiting the second reactor and entering the third reactor, and Ca3 is the final concentration that is exiting the third reactor. Why the CSTRs are being put in series? Because we are seeing that in steps the mixing up is better, the reaction is better, and at once if we make of some big volume, like if we make this much of a volume of CSTR, the conversion that it is going to give, the conversion is going to be much better if we do it in steps of 3, that is, use 3 reactors of some volume so that those 3 volumes combine up to make the bigger volume of the reactor. So instead of using this much of a reactor, we can break it into 3 sections and use 3 different reactors so that we can obtain a better conversion. We are going to see how it is being related with the conversion, and we are going to also find out if the reactor volumes are different, what is going to be the equation, and if the reactor volumes are same, what is going to be the equation. We are going to deal both ways. So let us first consider the basic equation of material balance, that is input minus output plus minus generation or depletion is equals to accumulation. So in terms of A, component A, what is the input? Q into Ca0, that is the inlet flow into the concentration of A. What is the output? Q into Ca1 from the first reactor supposedly, and plus minus generation or depletion. A is not getting generated, it is getting depleted, so it is minus RAV, that is the number of moles of A that is being depleted in the process, is equals to accumulation, that is ddt of CAV, number of moles of A that is accumulated in the system. Since there is no accumulation, it is a steady state process, so there will be no variance with time, so it is 0. So finally, with what equation do we reach to? Finally, what equation do we reach to? If I rub this, we reach QCA0 minus QCA1 is equals to minus RAV. Taking this on the side of the thing, taking the Q common. So CA0 minus CA1 by minus RA is equals to V by Q. Now what is V by Q? If we have a CSTR whose exit is closed and the entry flow rate is Q and the volume is V, the time that it takes to fill up the entire volume V with the volumetric flow rate of Q is basically V by Q. That is the time taken to fill up the CSTR if the exit is closed. So V by Q is defined as tau. Tau we keep the name as residence time or space time, whatever it may be called. It may be called residence time as well as space time. So this is going to be V1 by Q. This is my V1. So volume of the first CSTR. So we see that this is where we are finally ending up to. CA0 minus CA1 is equals to V1 by Q is equals to tau 1. That is for the first reactor. Now if we express minus RA as KCA1, CA0 minus CA1 by KCA1 is equals to tau 1. We get CA0 by CA1 is minus 1 is equals to 1 plus K tau 1, or CA0 by 1 plus K tau 1 is equals to CA1. So we are expressing the concentration from the first reactor exit in terms of the inlet concentration. So you are getting CA0 by 1 plus K tau 1. So if we now consider the entry to the second reactor, we are going to end up in, again in terms of an equation like this. That is CA1 minus CA2 by minus RA is equals to tau 2. Nothing but this, as similar to the first reactor, but only the inlet concentration is changing from CA0 to CA1 and the residence time is changing to tau 2 for volume V2 of the CSTR. So again, CA1 minus CA2 by KCA2 is equals to tau 2. So we see that CA1 by CA2 minus 1 is equals to K tau 2. So we are getting CA2 is nothing but CA1 by 1 plus K tau 2. So we know CA1 is nothing but CA0 by 1 plus K tau 1. So if we express CA2 in terms of CA0, that is the initial inlet concentration, my final equation that is going to come as, that is if we combine these two equations, replacing CA1 from this equation, substituting it, CA2 is equals to CA0 by 1 plus K tau 1 into K tau 1 plus K tau 2. Now if we consider for CA3, that is the exit of the third reactor, it is going to be another multiplication of K tau 3. So CA3 in terms of CA0, that is CA0 is equals to 1 plus K tau 1 into 1 plus K tau 2 into 1 plus K tau 3. So we are seeing that it is continuing a multiplication, and for CAN it is going to be 1 plus K tau 1 into 1 plus K tau 2 into 1 plus K tau 3 into 1 plus K tau n for nth CSTR exit. Now, if the volumes are same, that is of equal volumes, now we are going to talk about, since we have this equation of 1 Ca naught by 1 plus k tau 1 into 1 plus k tau 2 into 1 plus k tau 3, if we talk of equal volumes CSTR, then everything V1 is equals to V2 is equals to V3, that is same volume, which means since the Q is same for all the reactors, tau 1 is equals to tau 2 is equals to tau 3 is equals to, let it be tau. So what happens is Ca3 becomes a Ca naught into 1 plus k tau 1, which means 1 plus k tau, into 1 plus k tau 2, which means 1 plus k tau. So it is going to be a multiplication of 1 plus k tau into 1 plus k tau into 1 plus k tau. So it becomes 1 plus k tau to the power 3. So we are seeing for equal volume of CSTRs having equal volume in series, Can becomes Ca naught by 1 plus k tau to the power n. For unequal volume CSTRs, it is going to be 1 plus k tau 1 into 1 plus k tau 2 into 1 plus k tau 3, and it extends to the power n. So if we now try to express this thing graphically, where are we going to end up with? Express this graphically. That is, we draw minus Ra by Ca, supposedly this is the graph, and we know this is Ca naught. We draw a slope of minus 1 by tau 1, we reach Ca1. We drop another slope of minus 1 by tau 2, we reach Ca2, and like this we keep on continuing and keep on calculating the areas for getting the total area under the curve. This is the representation on a graphical level, and this is the representation on a numerical level if we consider it to be so. And remember, tau is nothing but V by Q for equal volume CSTRs, and tau 1 is equals to V1 by Q, tau 2 is equals to V2 by Q for unequal volume CSTRs. So as I was telling, for a single reactor having 3V volume, supposedly V1 plus V2 plus V3, 3V volume, what is going to be the case? That is, one reactor having this much of volume, that is 3V volume. Supposedly V1 and V2 and V3 is equals to V, 3V volume. So it is entering at Ca naught Q and is exiting at Ca Q, supposedly. So again, Ca is going to be Ca naught by 1 plus k tau, single step, and here tau is Ca naught by 1 plus k into 3V by Q, because it is 3V, and for this it is, that is the exit concentration from the third reactor is Ca naught by 1 plus Ca naught by 1 plus k V by Q whole to the power 3. Now for this reactor, that is, we are using the same volume, we are dividing into 3 equal volumes, that is, we are using 5, 5, 5 supposedly, and here we are using 15 in a single CSTR. Now if we are using 15, supposedly we are using 15 volume. So if we consider the same Q, if we consider the same K, if we consider the same initial concentration, and we are going to put this V, that is 15, and we are going to put this V as 5 whole to the power 3, we are going to end up with a greater decrease, that is Ca3 will be actually lesser than the Ca. That is a better conversion of the incoming A0. That is more consumption of A0 and more conversion to B. So what happens is, if we take a single reactor of 15 volume, we are achieving at the end is actually is greater than the concentration. That is, conversion is not good. Right? That is, if whenever the Ca is less at the end of the process, that is better. Lesser the Ca, that is a better conversion. We are getting that point. So this Ca is actually going to be more in case of a single reactor rather than using 5, 5, 5, 3, dividing into 3 equal volumes. Acting, the exit of one is the entrance of the other. That is reactors in series. That is, Ca3 is actually going to be less than Ca that we have calculated. So a single step reactor doesn't serve the purpose of reducing the A as much as the combination of 3 reactors in series that does. That is why we deliberately use or divide the volume into equal number of smaller volumes so that we can achieve it. Now we'll have to see various other things, that whether this is consuming how much amount of space, whether the lines are possible, the construction, the operational cost of the maintenance cost and the fixed cost to construct these pipelines, the valves that need to be fitted. We need to see a lot of factors in the industry before implementing it. And we are going to optimize the process so that this number of volumes of CSTR will be needed in series. That is, I think, would be enough for today. So we have to remember that we have to use CSTRs in series for a better conversion, to achieve a better conversion, that is depleting A to a greater extent. And this is the equation for CSTR in series of equal volume, and the equation for CSTR in series of unequal volume, we have already explained that, tau 1 plus k tau 1 into 1 plus k tau 2 into 1 plus k tau 3. And for a single CSTR of volume equivalent to the combination of 3 CSTRs in series, we are achieving this amount of concentration at the end, which is greater than the concentration here. So it is undesirable. We have to decrease the concentration because we want the more the consumption of A, the better it is for us. So we will have to use CSTRs in series. I think that will be it for today. If you liked our video, give it a like, give it a big fat thumbs up, and subscribe to our channel.